Can you see it now?
Yes. Yeah. So
Great.
yeah, perfect. So for the last talk of the morning or evening, depending on where you are, Michal Parnas is gonna tell us about testing intersectingness of uniform families with like a nice subtitle as well.
Yeah, thank you. So I wanted to say it's nice to be here, but we're not there. And anyway, this is a joint work with Ishay Haviv of a new result that we're going to present in the upcoming random conference. But I'm also going to tell you some stories about Dana. And as you will see also in this new result that Dana was not involved in, you can see her influence all over the place. So let's start with where I met Dana, where it all started. I think I hold the world record, at least in the room where you are at, of Dana years. I know her since 1984, so it's already 40 years. So I even, I beat Oded. Oded has more Dana hours, but I have the most Dana years. In any case, we both started for our bachelor's degree at the same time in the Hebrew University in Jerusalem in computer science. Dana also majored in physics, whereas I also majored in mathematics. And we didn't know each other that well during our bachelor's degree because Dana mostly hung with the physics crowd, which were much cooler, I think, whereas I was with the computer science crowd. But as we finished our bachelor's degree, we both came to our senses and decided that theoretical computer science is the thing to do. And then we continued to our PhD together and really had a lot of time together, a lot of fun. You can see here pictures of Dana from that time. I had a very hard time finding them. I mean, they're not my pictures, Oded sent them to me. You can also see the old CS building in Jerusalem and the Belgium house where you went to have coffee and talk about science. What you can also see is what you cannot see, and you cannot see a picture of Dana and myself. And believe me, I really looked hard, and it really bothered me. So I fixed the problem, and there you have it. So that's Dana. We now have a picture together, and I think I even became cool. And okay, so that's where we met. And just to get some sense of who Dana is, I want to show you the acknowledgements we wrote each other in our PhD. So Dana wrote, I had great fun working with Michal despite all her teasing. I tried to tone down the teasing during the years after I knew Dana better. And perhaps our robots can once come back to life. That's the first problem we tried to work on. We didn't succeed at the time. We had better success on other problems. And I wrote to Dana what I still believe is true, to Dana, who always saw the bright side of everything. And Dana, I mean, it's not that everything is perfect, but even when we're stuck with a hard problem, she says, let's continue a bit more and we'll solve it. It will be okay. And so I think this Charlie Brown Snoopy cartoon, the classic one, really tells you the different roles we played. And I tried to see the good side, the positive side in what happened to us now that we're here and you're there. So I modified this cartoon slightly, and now we have a new Charlie Brown Snoopy cartoon, which says as follows: our flight to Berkeley was canceled, missiles may fall on our heads, and Snoopy says, true, but at least we don't have jet lag, which, the time that this talk is happening, I'm not even sure about that, but this is it. Okay, so let's go on to the technical stuff. Oh no, before the technical stuff, our first paper together happened, our first success together in research happened when Dana returned from the States after her postdoc and told me all about this exciting new field called property testing. And we sat together over coffee, of course, and tried to think about graph properties that we can, find efficient algorithms for. And we thought about testing the diameter of graphs and realized really fast that it's not interesting in the previous models that existed, which Oded also talked about, I mean, the dense graph and the bounded degree graph. So we introduced the general model for graph testing, and then testing the diameter became interesting. And I think the name of our paper was terrible. We should have called it Introducing the General Model, but as you will see, during the years, we became wiser by choosing names. As to the other title of this slide, it's the evolution of property testing art. This screen beams, I think they were called, is the original picture we had in our PowerPoint presentation 30 years ago. Then we continue working on other property testing problems, clustering, metrics, and so on. And the art, as you see, changed into this green blob. Well, I guess it's supposed to be some general object. Luckily for us, WoLA came along and, art has progressed. Now we have a mouse. Okay, so now to testing intersectingness and this new result with Ishay. So just a short reminder of combinatorics, a basic combinatorics definition. A family of sets over the integers 1 through n is called intersecting. If for any two sets in the family, they intersect, their intersection is not empty. And this problem, testing intersecting sets, was considered about a year ago by Chen et al. And the first sentence in the abstract of the paper says, inspired by the classic problem of monotonicity testing, which of course is another result which Dana was involved in, and since then it really became a classic. And what Chen et al. Wanted to know is, can you test intersectingness of sets as efficiently as you can do it for monotonicity? Okay, so just two basic definitions that everybody knows, just that we'll have them on the slide. A family F is called of sets epsilon-far from intersecting if you should remove at least epsilon times the total number of possible sets, which is 2 to the n, so that it becomes intersecting. And we would like to find one-sided error testers, if possible, that should accept the family if it is intersecting and reject it if it is with high probability, if it is epsilon-far from intersecting. And the results that Chen et al. Had, they have both upper and lower bounds, which are almost tight. And as you can see from these results, it's completely different than what we know about testing monotonicity. So here the complexity is exponential in a square root of n. And so it looks different. And this is the place where Ishay and I got interested, and we asked ourselves, does it behave the same or differently if we look at uniform families of sets? So a family of sets is called K-uniform.
Sorry,
yeah?
I have a small question. What is the query model here? How do you access?
What? Sorry?
What is the query model?
The query, yeah, they assume that you look at the function, the family as a function, okay, where any set can be represented as a vector, and then you sample vector sets, and you get an answer if it's in the family or not in the family. So 1 or 0, depending. Okay.
Okay, thanks.
Yeah. So we assume the same model. Okay. Yeah. So a family is called K-uniform if all subsets are of the same size K for some K. And immediately when you talk about uniform subsets or families of sets, you should recall the famous Erdős-Corrado theorem, which states that if you're given a K-uniform intersecting family, then its size, the total number of sets in this family is at most n-1 choose k-1, okay? And they also show that the size of the family is maximized when it's a one junta. That means that all sets include some specific element I, as in the flower we have here in the picture, where all sets include the same element. Okay, so this is what we want to see. If we can find a more efficient tester than the one Chen et al. Had. Again, the model here would be, you have your family and you sample a set and you get yes or no, is it in the family, yes or no? Okay. So the first trivial question that one should ask is, of course, for what values of epsilon is testing K-uniform families even interesting? Is it interesting? Maybe it's like our diameter paper from back then that was not interesting at all. And over which universe is the problem defined? Okay, what is the domain? So if we look at the binomial coefficients, you have that n minus 1 choose k minus 1 is equal to k over n times n choose k, which means when epsilon is large, it's not very interesting. You can just sample, by sampling, approximate the size of the family, and using the Erdos-Rado theorem, just answer yes or no. So it's not very interesting. So epsilon has to be small for this to be interesting. Another point that you should notice that the size, because of this Erdos-Rado theorem, the size of an intersecting family is not that large compared to the whole universe of all sets of all size. Okay, so it's relatively small. And this means that it doesn't really make sense to look at it while sampling sets from the universe of all sets. And this is very similar, again, the name of Dana comes along, to what was done when testing graph properties, where you have three different models, the dense graph, the bounded degree graph, which Oded talked about, and the general graph that we have. And in all three papers, you can see Dana, of course. And a graph is said to be epsilon-far from a property if the number of edges should be modified, and it's a different quantity depending on the model. So we suggest here to look, as should be, I guess, at the universe that is just all sets of size k and not all sets of any size. Okay, and therefore, a family F is called epsilon-far, a K-uniform family. From intersecting, if at least epsilon times the total number of sets of size k, which is n choose k of its set, should be removed to make it intersecting. One last definition before I show you our results is the tolerant testing result that I had with Dana and Ronit in 2004. Where we wanted algorithms to be, we suggested that algorithms would be a bit more tolerant. That is, the algorithm should accept also objects that are epsilon-1 close to a property for some parameter epsilon-1, and reject objects that are epsilon-2 far from having the property. So we have now two parameters, epsilon-1 and epsilon-2. I'm not going to talk about this. Dana is going to give us a long talk tomorrow. But I am going to tell you later on the interesting secrets about this paper. So, but that will happen after the technical stuff. So finally, here are our results. As I said, epsilon should be small enough to make it interesting. Okay, so we're giving some for any fixed integer r, and for all integers n and k, where n should be at least 2k, otherwise all sets are intersecting and it doesn't make sense. There exist non-adaptive testers, okay? And then we have these four results. So we have both tolerant, two-sided error tolerant algorithms and one-sided error algorithms. For the tolerant ones, if epsilon-2, the parameter we're supposed to say no, if the object is far, is at least epsilon-1 plus k over n, then you get an optimal query complexity of 1 over epsilon-2. And if epsilon-2 is at least epsilon-1 plus this expression in the power of r, this constant r, then we pay a factor of log n, okay, times 1 over epsilon-2. And for the one-sided error case, you have, again, an optimal query complexity of 1 over epsilon. If epsilon is at least k squared over n, all this squared. And if you have it to the power of r, then you pay, again, a factor of ln k, this time times 1 over epsilon. Of course, you have the trivial lower bound of 1 over epsilon also in this case. And so we have here, the one-sided error in one sense it's better in this log k factor is smaller than log n. and of course it's one-sided. However, k should be at most square root of n for this to make sense, whereas in the tolerant case, k can be at most n over 2 or something like that. Okay, so these are the results we have. And now I want to show you briefly the idea behind the proofs. Stop me if there are any questions, but if not, I'm continuing here. So the first line, the tolerant, the easy part here, what you do is you just, as I said before, it's trivial, epsilon 2 is large, right? So what you do is just approximate the size of the family by sampling, okay? And then answer yes or no accordingly. So that's more or less the idea behind that. As to the second line, the second tolerant testing algorithm, what we do is use a result of Dinur and Friedgut, who showed that essentially any intersecting family is more or less almost contained in a junta for specific parameters. I won't get into that. So what you have to do is just sample, and estimate if your family is contained more or less in a junta, yes or no. And this requires this additional LAN and queries. Okay, so that's about the tolerant testing. And now I want to talk about this last line in the table, the general case of epsilon for the one-sided error algorithm. Okay, so here's our one-sided error tester. As I said, we show a one-sided tester for epsilon, which is at least this big. R is some constant with ln k over epsilon queries. Okay, there's a constant, by the way, a constant hidden here that depends on R somewhere. And what we do, as it happens many times in property testing, we just use the natural canonical tester, which means sample some sets uniformly at random. And for any two sets sampled, if they belong to the family, check if they intersect or not. And if all sets intersect inside the family, then you accept. Otherwise, reject. That's it. That's the algorithm. It's very simple. And it's easy to see that, of course, it's one-sided. It always accepts intersecting families. Okay, so now we're left with the difficult side of the proof. And that is to show that if the family is far from intersecting, then this natural algorithm will reject, or in other words, it will find with high probability a pair of sets that do not intersect. Okay, so this is what we want to do. So here's the proof idea. Let's assume that our family is epsilon-far from intersecting. First, one trivial fact, that the size of the family should be at least epsilon times n choose k. Otherwise, you can just delete all sets from F and you get the empty family, which is, of course, intersecting. And recall that epsilon is this large, at least this big. And let's assume that somehow magically, for every small subset A, okay, of the integers 1 through n, whose size is strictly less than r, so A is small, right? We sample some subset S sub A in the family, somehow we manage, such that the subset does not intersect with A. So S sub A intersection with A is empty, okay? So assume this happened. It doesn't have to happen, but let's assume for now that it happened. What we can show now is a combinatorial lemma. It's not difficult, you do it by counting, careful counting, that the number of sets of size k, S, that intersect all this small subset S sub A is at most this expression, okay? So never mind, you just count and it turns out okay. So if this lemma is true, and it is true, what you do now is just, plug in the parameters and it works out. You know that F is at least epsilon times n choose k. Put the value of epsilon. Epsilon is at least k squared over n times r. So replace epsilon with this. So you get that f is at least this omega expression, okay? But by our lemma, the number of sets in the whole universe that intersect the small sets that we sampled is less than this expression in the omega. And this means that after a few more samples, we'll get a set S in our family that doesn't intersect at least one of these sample sets and will reject, okay? So all this works if our assumption holds, okay? But of course, it doesn't have to hold. There may be some small subset A of size less than R, such that for all our sample sets, they do intersect with A. And so we cannot use our lemma and everything fails. So when does this happen? Maybe we were not lucky, but most likely this happens if the small subset A intersects with most of the sets in our family. So such a subset A, we call it, we say that it epsilon captures the family, okay? If the number of sets in the family which do not intersect with A is small, is relatively small, at most epsilon times n choose k. So the subset epsilon captures our family if it intersects most of the sets in the family. So for example, in this picture, if A includes the elements 1 and 2, and these are the circles are your sets, then you can see that all the circles, but this purple one, I hope it looks purple where you are, but in any case, all the sets besides this one circle intersect with A either in 1 or in 2 or both 1 and 2. Okay, so A captures our family. So assuming we have such a set A, which epsilon captures our family, and our family is epsilon-far, we are now in the situation where our family is epsilon-far from intersecting, then what we can show is that there exist two subsets, B and C of A, okay, which are disjoint. B and C are disjoint, such that we can find, in our family F, two subfamilies, F1 and F2, where F1 includes all sets whose intersection with A is B, F2 includes all sets in the family whose intersection with A is C, and these two subfamilies contain many sets between them who do not intersect, okay? Or in what we say combinatorially, these two subfamilies are epsilon prime far from cross-intersecting. Epsilon prime is slightly smaller than epsilon. So if we look again at this picture, and assuming that we had the family, a small set, 1A equals to 1 and 2, which captures our family, we can find the set B, which includes the element 1, C includes the element 2, and we place in the family F1 all sets which include this element 1, that is their intersection with the A is exactly B. We place in F2 all sets of the original family whose intersection with the A is exactly 2, the set C. And if we place an edge between any two sets that do not intersect, far from cross-intersecting means that there are many edges between the two sets, okay, between the two families. So what we want to do now is say the following: if F is indeed epsilon far from intersecting, and you have such a set A that captures your family, then there will be many edges between these two subfamilies. And now what we have to show is that our algorithm will sample a pair of disjoint sets, one from F1 and one from F2, and reject. So how do we do this? The proof is almost over. One more slide. How do we do this? In the same way. We look now, we have our two subfamilies, F1 and F2, and let's assume that for any small subset, A prime this time, that doesn't include the elements of A, which is smaller than R, we sample some subset S A prime on this side, on the side of F2, which does not intersect with A prime. Okay, so let's assume that happened. Again, we can show that the number of sets, this time from the other side, from the side of F1, that intersect all these sets from the side of F2 is small. And this means that after a few more samples, we'll get a set S in F1 that doesn't intersect one of these sets in F2, and we'll reject. But what happened? Again, we assumed something, right? So there may exist a set A prime that captures F2. So what we do now, we refine this set F2 again and so on. It cannot go more than R rounds, and finally the proof works. There are a few more technical details over the way, but that's basically the idea behind the proof. Okay, is this okay? Makes sense? Fine. Okay, I'll skip the proof of the lemma, and what I want to tell you now are more Dana stories, since you had enough science for this morning. And I want to come back, return to our tolerant property testing paper. Dana and I were visiting Ronit in New York. Ronit was then in New York. And this is Ronit Emran's apartment is, up there, right, Ronit? I think it was the top floor, if I'm not mistaken. And we were thinking, right? Did Ronit say yes?
Oh, yeah, she said yes and told us which level.
Okay, good. Yeah, so it was the top floor. I think I remember that.
No,
okay,
not the top floor. Not the top floor.
Not the top floor? Oh,
second to top.
Second to top. Okay. No elevator. Yeah, it was very high. Very high. Anyways, so yeah. And there's this psychic, by the way, in the building next to it. There's, I don't know if you see Chelsea Psychic. I remember that. Anyway, we were visiting Ronit, and the three of us were sitting there, top floor, next to top floor, whatever, and thinking we should, find something new. And we thought maybe we should make algorithms, and I'm not going to use the word tolerant because tolerant didn't exist then, but I don't remember which word you said, more forgiving, let's say, okay? And we thought about the clustering problem, where, even if you cluster most points, you're supposed to be happy. If 2 or 3 points are not clustered, you don't want to reject the object, right? So we wanted the algorithm to be more forgiving, and we decided it's a great idea, but decided that we're not going to make the same mistake that Anna and I made with that diameter testing paper that had the wrong name. And we said we should find a good name. And not only a good name, we had a great idea. We should have a good name like the PCP theorem. Now, the PCP theorem was very famous by then. And it's really a great name, right? Why is it great? First of all, the first letter of PCP is right, like the third letter. So you have this acronym which sounds nice, right? PCP. Besides that, it's a drug, so that makes it even, it's even better. No wonder the PCP theorem became famous. So we wanted such a name. So we sat there for an hour tossing names around until the name tolerant, came about to be. And first of all, we already have the 3-letter thing where the first letter is like the third letter, right? Tolerant property testing, TPT. We're halfway there. And we Googled it to see if it's a drug. It's not a drug, unfortunately. Well, we did see that it has to do something to do with transportation, but that was it. So we said, okay, let it be tolerant property testing. And that's how the name came to be. And while preparing this talk, I decided to see if this acronym became more famous since then. Then it was just transportation and us, okay? So this is what I found. There you have it. You have all these great acronyms. We really became famous, Ronit and Dana. And, we have this retirement solution, which is good for the 60th birthday, TPT. My favorite is Throat Punch Thursday. It turns out to be a thing. It was invented after us. We were in 2003 or so. They were in 2004. Turns out you can go and punch people on Thursdays, It's crazy. Okay, anyway. So that's one secret about the tolerant property testing paper. And now I'm going to tell you the next one. And Ronit, you probably know the answer, so please do not tell everybody what the answer is. So the question is, who is Tess? We have this acknowledgement in our paper that goes as follows. We acknowledge the contribution of Tess in our attempts to obtain an improved tolerant testing algorithm for monotonicity in higher dimensions. So we had this acknowledgement and we sent the paper to be reviewed. And after a while, the reviewer returns this comment. It was reviewer 2, it's always reviewer 2. And I mean, they had also good comments, right? But this was the comment. I do not know who Tess is. Please put in her or his full name. So when it was in the States back then, and I called Dana and I tell her, what are we going to do? Really? I mean, this is a problem. And we discussed it for a bit and decided we'll just tell the truth. So this is the reply we wrote the reviewer. Tess is a dog and therefore does not have a last name. And just so everybody knows, Tess was my dog. And while I was walking with her, I got some of my ideas. I'm not even sure the ideas I got with Tess were that great, but anyway, she got an acknowledgement. And one last Dana story, if I'm showing Tess. So Tess is sitting here in this great dog bed, which Dana got her, by the way. And this happened after I had my son Asaf. Dana said she wants to get something as a present. I told her you don't really have to. And she asked, what do you get? I said, I don't know, baby things, toys. And Dana says, no, I want to get Tess something so she wouldn't be left out. And this is who Dana is. So thank you for that bit. Tess appreciated it. And Dana, by the way, is a cat person. So this makes it even more special. Okay, just open problems to finish the talk with. This is our results. The trivial open questions are, of course, are these log factors necessary? And find optimal testings for all values of epsilon, not only for this strange expression. And maybe a more interesting problem is find other interesting properties with the complexity gap between the general and uniform case, because as you can see, our algorithms are efficient compared to the algorithm of Chen et al., which were exponential. Okay, so there is this gap. That's it. Happy birthday, Dana. I hope we have many more years of research and mostly friendship. Thanks.
Thank you. Any question for Michal? I'd like also to thank Oded and Michal for staying up late to give that talk.
Yes.
Thank you. And
You're welcome. I hope you have fun.
Thanks. And one small announcement: we're actually gonna start again at 2:30, so that you actually have time to find food and before coming back. And that's an extra good news. That means you will hear myself a little bit less because I'm gonna use my talk as a buffer. So yeah, so we'll see you all at 2:30 here, and we're gonna start, I guess, on the clock then.
Bye, everybody.
Thank you.